Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll. Last week we talked about geometry and topology. These were clearly mathematical ideas, but I think that most people know these are ideas that have a big role in physics. So today, since we did math last week, we're going to do math again, okay? We're going to talk about symmetry. Now, symmetry is a quintessentially physics topic. Symmetry is at the heart of a lot of modern physics, but the way that we describe symmetries is going to involve some math, and that's basically what today's big idea is, how we go about actually describing symmetries. If you've ever heard of the standard model of particle physics, you may have been told that it's based on a symmetry group, SU3 cross SU2 cross U1. So at the end of this, maybe not today, but at least today or next week, we're going to understand exactly what that means to say that the symmetry group of the standard model of particle physics is SU3 cross SU2 cross U1. Those letters, those symbols, SU3, etc., correspond to internal symmetries. So they're actually transformations. They're basically generalized rotations of different fields in the standard model of particle physics. So the quantum field theory will come into play. We also have what are called external symmetries, I guess. Are they called external symmetries? They're not internal symmetries. Space-time symmetries is what I'm talking about. We know that, for example, you can translate where you are in space, you can rotate where you are, you can change your reference frame in special relativity. All of these are also symmetries. So this is why symmetry is so crucial in modern physics. But what is it? What do we mean? So this is the kind of thing that mathematicians do, right? They take an idea that you have and you think you understand it at some intuitive level, and they try to formalize it, make it precise, and then talk about its properties in general circumstances, far abstracted from any specific application. Then the physicists come back in and say, I bet I can find an application for that. So that's what goes on with the study of symmetry. So what do we mean? Let's get into what we mean by symmetries by starting with some examples. Just draw some shapes on the iPad here, and you can judge for yourself how symmetric they are. So here is a completely non-symmetric little blob. There you go. I don't see any symmetries there at all. And look, I've been practicing for you folks. Don't say I never did anything for you. I've been learning new things on notability here. Watch this. Triangle, but boom. It becomes all nice. Now I want to make an equilateral triangle. There you go. Hopefully that's an equilateral triangle. Okay. That seems to have more symmetry than the blob. Like somehow there's some regularity there that we would like to be able to understand better. Likewise, we could draw a square. There you go. Hopefully that's really a square, not just a rectangle. But again, some symmetry there. And what if we could also draw a circle? This is going to be harder to draw, but I can do it. And there we go. There's a circle. Okay. 4 different shapes, and I've arranged them in what I will argue is order of increasing symmetry. There's more symmetry as you go from left to right. And that kind of has an intuitive sense. The circle in particular looks extremely symmetric, right? It looks the same from every different angle. But this is what helps us turn these vague ideas into something formal and manipulatable at the level of equations and theories of physics. We want to know exactly what we mean when we say there's more symmetries in the circle than the square, more symmetries in the square than the triangle. And we kind of already gave it away. The idea that you can look at the circle from any different angle is a reflection of the fact that there's some symmetry there. The symmetry is a way of saying that there's a transformation we can do to some object, to some system, that leaves the essential features of the system invariant. That's what symmetry is. I'm not sure if that's the technical definition. Well, sorry, I'm sure that is not the technical definition. But a symmetry is a set of transformations, which means, in mathy terms, a set of maps from the thing to itself, a set of ways you can manipulate the thing back to itself, transformations, that leave, let's just say, leave the system, whatever it is, invariant. What we mean is leave whatever we count as the important features of the system invariant. So to make that a little bit more specific, think about the triangle. We can clearly rotate the triangle by 120 degrees, right? If you rotate it by 120, it goes back to the same triangle. You can rotate it again, another 120, 240. Then you rotate it a third time and you get 360 degrees. It's back to where we started. So let's actually make that explicit, okay? So here's another triangle. we're gonna, that was not a very equilateral triangle, but I'll try to fix it. There we go. Pretty close. Here's our original triangle. I'm going to duplicate it a couple times. And here's my original triangle again. Duplicate, good, put it over here. And this will all make sense why I'm doing it in this particular way. And I'm going to label the vertices, okay, A, B, C. I can label them anyway. The labels are completely arbitrary. It's up to me. I just want to keep track of what I do to the triangle, because the whole point of the symmetry is I'm going to do something that makes it look the same. So A, B, and C are not labels that we physically stick onto the triangle. They're just to remember what we've done to it, okay? So what I mean by this is we could, for example, rotate clockwise 120 degrees. So that's 1/3 of the way around the circle. And I'm going to call that operation R plus. The notation will make more sense in a second. So what R plus means, rotate 120 degrees. So I get C, A, B. Okay? That's what I mean by that particular rotation. So you see that if I had rotated by 90 degrees, I would have gotten the triangle off at some angle, 90 degrees. Whereas if I rotate by 120 degrees, I get exactly back to where I started. If I were really fancy about it, watch what I could do. I could take the triangle and I could rotate it. And this is why I'm not doing it in real time, because it kind of becomes messy and distorted. But that's the point. It takes the 120 degree rotation to come back to where it started. That is part of the symmetry. We can also rotate backwards. So we can do R minus. I'm not going to clutter it up again, but that's a counterclockwise rotation by 120 degrees. So that gets us to A, B, C. And we see that these three versions of the triangle are labeled differently. So the triangle looks the same in every case, but it results from a non-trivial transformation on the original triangle. So this is part of the symmetry group, as we're going to call it, of the triangle, the set of transformations that we can do to the triangle that leave it invariant. Now, of course, I could do a rotation twice, right? I could do R plus twice, and that would actually get me to R minus, right? If I did R plus again, I'm not going to draw it here because it'll clutter up the diagram, but if I rotated this triangle, this one right here, if I rotated that by another 120 degrees, I would get this triangle over here. So these are the two rotations that I can do. But I'm not done with the triangle, because there are things I can do other than rotations, right? So to see that, let's make some more triangles here, okay? And I'm going to put these triangles down here. Not easy to do this, but you know, we're learning, trying to get better at it. There you go, 3 more triangles, and it'll be clear in a second why there's 3 more triangles. The point is that in addition to rotating, I could also flip the triangle, right? Like there's nothing that says that I'm confined to moving in the plane of the iPad or of the board I'm drawing on here, right? I could flip around some axis. So if I flip around this axis, for example, I would get A, B, C. Whereas if I flip around this axis, the original triangle, I would get C, A, B. And if I flipped around this axis, the original triangle, I would get B, A, C. And you can notice that every one of these, if you look at the vertices and how they're labeled, they're all distinct from each other, okay? No 2 of these 6 triangles are exactly the same. When you consider, I mean, all the triangles are exactly the same. No 2 of them result from doing nothing to the triangle. They're all a non-trivial transformation, okay? So we can label these. Let's call this, let's call it a flip. We have flipped around the vertical axis. It's more typical to call it a reflection, but we've already used the letter R for rotation. So let's call it a flip. Let's call this F1. Let's call this one F2. And let's call this one F3. There you go. So I think that's it. You can check at home, but I think there's nothing else you can do to the triangle that does not get, that gets something different than all of these different possibilities. In fact, I'm sure of it because in this one particular case, the triangle is the one case where the set of symmetries of the triangle, the geometric shape, is just the set of permutations of the 3 vertices, A, B, and C, okay? That wouldn't be true in a square or a pentagon or whatever, but it's true for the triangle. So if I just enumerated A, B, C, A, C, B, etc. There are 6 of them, and they correspond to these 6 versions of the triangle. Okay. So those are the symmetries of the triangle. How many of them are there? You might say, well, there are 5 because we got the first rotation, the second rotation, and the 3 flips. But in fact, there's a 6th because we can do nothing. We can just transform the triangle onto itself. That's an important thing we can do. Namely, we just leave it as it was. So I will label that by the fancy number 1 here, the identity operation. Leave the triangle invariant. So I really have 6 things I can do to the triangle if I include doing nothing as a thing that I could do. So there's a lot of information here. There's a lot of structure going on here. This is what makes mathematicians excited about symmetries, is that you don't need to simply go ahead and enumerate all the different possible symmetry transformations. You can talk about how they relate to each other and what kind of structure they form. So together, these 6 transformations, and we'll list them. The identity, rotation clockwise by 120, rotation counterclockwise by 120, flip around one axis, flip around the other, flip around the third. These 3 form a group. That is what the technical definition of, the technical term that we attach to this kind of mathematical beast is. A group is a little bit more specific than just, say, a set. It's not just a collection of things. A group forms some very specific properties. The crucial feature of being a group is that you can take these transformations and combine them, and you will always get something that is another transformation that is already in the group. Okay? This is called the closure property of the group. The fact that you can combine transformations, you never leave the set of operations. So let's see that in action a little bit. Consider if we start up here at the original triangle and we do flip 1, so we go around the vertical axis, so we get down to here. I claim that I can get to flip 2 by then doing a rotation. So if I go over here, what do I need to do? I need to get, starting from here, to get to here, I need to move A down to the left, C up to the bottom right. It looks like I'm going counterclockwise, which is in fact the rotation minus, R minus. That is what we called it. So what this means in equations is we would write this as F2 equals R minus F1, okay? So the order matters here, as we will see in a second. So you read from right to left, first do F1, then do R minus. Why? Why do we do it in that order? Well, because you're supposed to be thinking of these things not as numbers that you're multiplying, but as operations that you're performing on the triangle. So when we do something like, let's just do an example, F1, acting on the triangle, here's the triangle that we start with A, B, C. That is flipping around the vertical axis, and so that gets us A, and here's the triangle, and then we get B and C, okay? So the reason we read from right to left when we combine these transformations together is because we're imagining them acting in turn on the triangle itself, and the one on the rightmost is the one that acts first, and then after that, we go leftward. Let me erase all this stuff because it's just going to get in the way, but that's why we go from right to left. Okay, so when you can check at home, whenever you combine 2 of these transformations, you stay inside the group. That's a crucial property of being what it means to be a group. The other crucial properties are there's an identity element. Okay, there's one element that doesn't do anything at all. And the other one is that there's always an inverse to any operation. So there's always one operation that can be undone by a single element of the group. So for example, here we would say that R plus is the inverse of R minus. Okay, it's R minus to the minus 1. Another way of writing exactly the same thing is that R plus times R minus equals the identity element. R minus followed by R plus would get you back to where you started. And you can check that that's true. It is true. Okay. What is not necessarily true, and sorry, there's another technical thing about associativity. How you put parentheses around your group transformations does not matter. This is what it means to be a group. A group is a little bit more elaborate than a set. This is the kind of thing mathematicians do. They start with a set of things, and they put structure on them, and they say that structure obeys different conditions. The structure here is the way to combine transformations together. It's the multiplication rule, if you like. That multiplication rule need not be what we call commutative. Commutative means you can change the order of operations, and it doesn't matter. So here it clearly does matter. If we took not f1 followed by r minus, but r minus followed by f1, okay, well, that would start us here, the original triangle. We go r minus, brings us here. Flipping by f1 means that we flip around the vertical axis, so we would flip a with c, so we get bca, which is not down there, it's over here, right? So that equals f3. Look at that. So r minus f1 does not equal f1 r minus. They do not commute. And the lingo, we don't need to really know it. I mean, we might need to know it. Commutativity, commuting groups, if things commute, if the order doesn't matter, sometimes that's true, are called abelian groups, after Professor Abel. And guess what? Non-commuting groups are called non-abelian. So you can see why mathematicians would fall in love with this. You have this beautiful structure, they fit together, you can define things, you can ask questions like, do the different transformations commute or not, and so forth. So this is the whole subject of group theory, and it is the sort of mathematical version of what physicists call symmetry transformations. It is a fact of the world that we have symmetries in the world, and is a mathematical fact that the way of describing them is by talking about groups. Now, there's just a couple other things that I can't resist telling you because this is an infinitely interesting subject. Remember, the point of the group is that different transformations combined together will always give you another group element, okay? So we can have subgroups. We can have subsets of the original group, which are themselves groups. So for example, if you have the identity element and the two rotations, r plus and r minus, they form a subgroup. So that's the subgroup of the top three things right here. If you rotate and rotate backwards, you're never going to flip. A flip is a whole separate thing, okay? So this is a perfectly good subgroup. If you combine r plus and r minus, you will get each other. In fact, what you would do if you were being very careful about this is you would write out the multiplication table. So we already said that r plus times r minus is just the identity, but you would also write out things like r plus squared, which is, guess what? R minus, as you can go back and figure it out, okay? I'm going to erase that because I'm not done writing down subgroups. But that's the kind of thing you would do. So this is a subgroup, good, but what about just the identity and r plus? That is not a subgroup. I'm going to make this red, okay? Big red X there, not a subgroup because r plus times itself is not in that collection of things. It gives you r minus. There you go. Likewise, if you have just the identity and one of the flips, pick any one, f1, f2, f3, is this a subgroup? Okay, well, you can go back and look. I could start here in the original triangle. I could flip it by f1. If I flip it again, I just get back to where I started. So indeed, this is a perfectly good subgroup. f1 squared, because f1 squared equals the identity. That's all you really need to know. Whereas, if you try to complicate your life, what if you said 1, f1, and f2? Okay, so you have two different flips. Where does that get you? Well, so you start here. Here's nothing. Here's f1. I flipped around the vertical axis. If I do f2, that's going to flip around the axis going this way. So it's going to flip a and b. So I'm going to get b at the top, a at the bottom left, c at the bottom right, which gets me here, which is the r minus element, which is not in the group that I just wrote down. So this is not a good subgroup. So you can see how there's sort of an interesting set of possibilities. What is a subgroup? What is not a subgroup? One last little fact, you can talk about, take two non-trivial group elements, say r plus and f1. It turns out that all 6 of the elements in the group can be written as some combination of these two. So these are called the generators. It's a choice of what the generators are. There's other choices. The generators of the group transformation, from these you can build up the entire group, okay? I mean, I can go on. There's other things we can say about all of these things, but you see why groups are so important. Groups are the way to mathematically represent the idea of symmetry transformations. Okay. Just to be, one fact I really should tell you here. These groups all have names, okay? And I kind of don't want to like dwell on the names. This group is called D3, the dihedral group of an object with 3 corners. So as you might guess, there's something called D4, which is the symmetry group of the square, D5, which is the symmetry group of the pentagon, etc. And this happens to equal S3, which is the permutation group of 3 elements, ABC, right? So ACB, BAC, etc., are all different symmetry transformations of those 3 elements. In general, as we said, the dihedral group is not going to be equal to the symmetric group on n elements, because if you have a pentagon, you're not going to be able to do all the different permutations of its vertices. Those are just the words. Who cares what the words are, what the symbols are, what the notation is? What we care about is the essence of it. But when it comes to these little examples, there is another couple of examples where knowing the terminology will help. So there's a group called the integers. Actually, it's not called the integers. Let's be careful. Z, this fancy Z, is how we denote the integers, and it equals, dot dot dot, -1, 0, 1, 2, dot dot dot. Okay, you know what the integers are. When I say the integers are a group, what's going on there? It means I can add them together. If I take 0 plus 1, I get 1. If I take 1 plus 2, I get 3, etc. So if I think of the integers as a shift of a real line, so let's imagine that I have some real line. I literally take the integers, or any set of points equally spaced, and I call each element of the integers a shift by that much. That is a symmetry transformation on this set of points, okay? But notice that I do, in fact, fulfill all of the requirements. The integers, if I take any 2 integers and add them, I get a third integer. There is something called the inverse of any integer, namely minus that integer. And there's also an identity element, the number 0, okay? But we have baggage about the integers. We think that not only can we add them, but we can also multiply them. 2 times 3 equals 6, okay? So you might say, well, maybe there's another thing I can do, a different kind of transformation in the integers that I could do to make a group, namely multiplying them, not dividing them, or not adding them. False. That doesn't work. I'll give you 3 seconds to think about why it doesn't work. It doesn't work because you need an inverse to define a group. So if I have plus 1 as my transformation, then I have -1 as my inverse transformation. Whereas if I do multiplication, I can multiply by 0. And I can't undo that. If I take an integer like 6 and I multiply it by 0, I get 0. And there's no way to multiply anything by 0 to get back to 6. So it's the integers under addition that are a group, not the integers under multiplication. So when we say, in this kind of context, just the integers, we generally mean under addition. The integers have an infinite number of elements in the group. There are infinite numbered groups, and there's also finite numbered groups, like this group up here. The triangle group, or the dihedral group, has 6 elements. The integers have an infinite number. But there's a version of the integers that only has a finite number, namely the integers modulo n. And what that means is we define Zn. We define addition on the integers, but only up to n. So if you get above n, whatever n is, you pick it. So there's Z2, there's Z3, Z4, different versions of this group. You just say, 1 plus 1 equals 2, but if you're doing addition modulo 2, you say that 2 is the same as 0, okay? So Zn is just the set 0, 1, 2, dot, 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 n minus 1. Once you get up to n, you wrap back around. So Zn is very much like a circle. Let's make it a circle, where you've written n points. Okay? So this is Z6. And there's an element, there's another element, etc. Okay? You come back to where you started. So these groups here, this one, is isomorphic, the same as Z3, whereas this group here is the same as Z2. Okay, so these are abelian groups. If you notice, I can, that doesn't matter what order I do R plus or R minus in. It doesn't matter if I only have two elements in the group, it better be abelian. There's no way that it could not commute with each other. But so these are two very, very important discrete groups, okay, discrete sets of transformations. Now, you notice there are an infinite number of different groups called the integers modulo n, one for every single value of n greater than 2, or 2 or greater, every single integer. So you could have z a billion or whatever. As in terms of finite groups, it turns out they're classifiable. There's only a finite number of ways to be a finite group. There are an infinite number of finite groups, like Zn, but this is only one way to be a finite group, and there's only a finite number of ways. And it was only like in 2004 they finally classified this. There's both these continuous families of finite groups, and there's also what are called the sporadic groups. There's some weird ones. There's something called the monster group, which has something like 10 to the 53 different elements. And so, of course, mathematicians just love this stuff. Physicists like the integers and the integers modulo n as groups. They like the dihedral group or the symmetry group of the sphere, of the triangle. But what they love are continuous groups, okay? So that's where physics becomes really exciting. Continuous groups are just what they sound like. They're groups where there is some continuous transformation, a transformation that is indexed, if you want, by a real number or by some smooth parameter, some continuous parameter, not by an integer or just some number. Continuous groups, also called Lie groups, after Professor Lie, who studied them, classified the earliest ones. Okay, what's an example of a continuous group? Well, remember we had the circle, right? Remember we had, oops, that's not a very good circle there. Can I fix it? Is it fixable? Yes, look at that. Kind of like a circle now. A circle you can just rotate by any angle, right? Any angle between 0 and 360 degrees. Or we're going to have to update our units here. Sorry about that. But we're going to have to go to radians instead of degrees. So I'm going to have to teach you about radians if you don't already know. Radians is just degrees times 2 pi over 360. So a right angle equals pi over 2 radians. All the way around the circle is 2 pi radians. This will become clear why this is important in a second. It's just units, just a choice of units, okay? But physicists, mathematicians are always going to be using radians rather than degrees. I've been shielding you from that to some extent, but now we're going to have to go there. So anyway, any rotation of the circle by between 0 and 2 pi radians is a symmetry transformation. So there's a continuous group, an infinite number of different possible angles by which you can do that rotation. And in fact, to some extent, the basic most important Lie groups are in fact generalizations of this idea of a rotation group, okay? In particle physics, as we'll get to in a second, we have SU3 cross SU2 cross U1 in the standard model. Yeah. And these are all examples of continuous groups that are sort of generalized rotations in some sense. So let's do this a little bit more systematically. Let's look at that continuous group, which is called the symmetry group of the sphere. Of the circle. Circle is, of course, a sphere. It is a one sphere. It's a one-dimensional sphere. But I will call it the circle. So what are the symmetries of the circle? Well, very similar to the analysis for the triangle. Any rotation, well, we have the identity. We have any rotation by any angle theta, with theta being an element of 0 to 2 pi. Oops. So including 0, not including 2 pi, because you can't include 2 pi because it's already there for 0, okay? In fact, we shouldn't even include the identity element, because the identity element is there, but it's a rotation by 0, okay? That's what it is. And there's another one. There's another, can you guess what that is? Yes, you can. A flip around some axis. So you can write some axis, and you can imagine just flipping antipodal points on opposite sides, okay? We kind of implied the existence of something like this transformation when we did the identification of antipodal points in our topology discussion last time. So together, these are called O2. That is the letter O, not the number 0. 2 for a two-dimensional plane where the circle is living, and O for orthogonal. This is the orthogonal group. Orthogonal. And in general, ON is the set of rotations. Oof, once again, a bad handwriting day. Sorry about that. Rotations and reflections in n dimensions. So the circle is a one-dimensional object itself, but if I erase this bit inside here, just to make my life easier, the symmetries of the circle are the same as the symmetries of rotations around a point in the plane. So the plane itself is two-dimensional, right? It has two-dimensional vector space. You rotate around the center. That is the orthogonal group in 2 dimensions, okay? So in this case, and in fact in every case, what's going to happen is ON, the entire set of symmetries of this n-dimensional space, the generalization of a rotation, is going to be rotations. So, sorry, let me just be a little bit more explicit about it. It's going to be something which we call the special orthogonal group. So this is just rotations times Z2 reflections or flips. This is always going to be true. So just like the triangle, you could separate out the rotations and the flips. You can just do that in general in any number of dimensions for any orthogonal group, for the continuous symmetry group in n dimensions. So generally that's what we do. We don't usually talk about ON. We could, but the point is, once you get to the math of it and the physics of it, if you can separate out a group into 2 different kinds of things and then combine them together later on, that is almost always a sensible thing to do. There will be things that are invariant under just SON and not, oops, that's a Z2. Sorry, it's just a 2 element group, not an infinite number. Anyway, there will be things, not necessarily this plane, but there will be things that are invariant under SON, but not the Z2 flips. So whenever you can sort of separate out these groups into separate pieces, that's different kinds of transformations, that's generally a good thing to do. Okay, so then this generalizes, right? We have, for example, SO3 are rotations in 3 dimensions. That's not a generalization, this is an example. In 3D. So think of, a 3-dimensional space parameterized by 3 vectors, and you can rotate it. You can rotate it to be wherever you want, right? So if we started with bases x, y, z, then you rotate and you get something x prime, y prime, z prime, and every single possible way to rotate that is an element of SO3. So even though there's an infinite number of such rotations, what you can do now is not talk about the number of transformations, but the dimensionality of the space of transformations. So O2, let's think about it. Let's see if you can guess. SO2 is the rotations in the plane. Okay, this is SO2. How many dimensions, not is the thing we're rotating, but is the group? How many dimensions is the group SO2? Well, the answer is it's just one-dimensional. There's only one thing we can do. So we're rotating 2 dimensions into each other, but there's only one way to do it. And therefore, SO2 is a one-dimensional group, okay? In fact, the group itself is just the circle, topologically. SO3, it turns out there are 3 ways to do it. And basically, you can think about that as you can rotate around this axis, around that axis, or around that axis. So this is a 3-dimensional group. And that sometimes confuses people into thinking that somehow the number of rotations should equal the number of ways you can, the number of dimensions in the thing you're rotating. But that's not the case. So if you have SON, that is rotations in n-dimensional space, but the dimensionality of SON works out to be 1/2 n minus 1. Okay, so if you plug in 3, you're going to get back to where you started, right? 1/2 times 3 times 2 is 3. But if you plug in 4, 1/2 times 4 times 3 is 6. So 4 does not equal 6. In general, once you get beyond three-dimensional space, the number of rotations is bigger than the number of dimensions you're rotating. You might wonder how that can possibly be true. Isn't it always true that you just be able to rotate around an axis? But that's not true. This is just because your ability to visualize in dimensions greater than 3 is failing you. When you rotate in 4 dimensions, you don't rotate around an axis. You rotate around a plane. So a rotation moves one axis into the other, leaving all the other axes invariant. So that's the question you should be asking yourself. How many different ways are there to leave all the other axes invariant? And the answer is this. So all that is just to say SON, the group of rotations in n dimensions, is not n-dimensional. It has a bigger number of dimensions. Okay. Now I'm going to complicate your life a little bit. Okay, the rotations is a pretty obvious thing. It is a non-abelian group. Other than SO2, where it's just rotating in the circle. Once you start rotating in 3 dimensions, the order matters. If you rotate a little bit around the z-axis and then a little bit around the x-axis, you can convince yourself you're going to end up with a different orientation than if you rotate a little bit around the x-axis and then a little bit around the z-axis. It's a non-abelian group. Most groups are not commutative, are not abelian. Also in physics, many things turn out to be complex numbers, right? We don't use real numbers all the time. We sometimes use complex numbers. And vector spaces can be either real, by which we mean we take basis vectors and take linear combinations of them with real numbered coefficients, or they can be complex. And there's other alternatives also, but they can certainly be complex. Let's put it that way, which means that our vectors are sets of combinations of basis vectors, but the coefficients of those basis vectors are complex numbers, not just real numbers. So there's a version of rotation groups that applies to complex vector spaces, and we call those unitary groups, for reasons which I'm not going to reveal. So the unitary groups, UN, are symmetries of complex n-dimensional spaces. Just like ON were the symmetries of real n-dimensional spaces, UN are the symmetries of complex n-dimensional spaces. So just to be a little bit more explicit about that vector stuff I just said, a real vector means, you might have seen things like this. You have a vector, and you say, A times the unit vector in the x direction plus B times the unit vector in the y direction. If you're in 2 dimensions, if you're in 3, then you might have C times Z. And implicitly, A, B, and C are all real numbers. Okay? I don't need to be quite that mathy. I just said a correct thing, but you don't need to be mathy unless it is necessary, right? So A, B, and C are real. There you go. Whereas in a complex vector space, same exact notation, okay? V equals A, and because space, the 3-dimensional space we live in, is a real vector space, okay? We locate where we are using real numbers, not complex numbers. I hope you've noticed this in your life. So I'm not going to write x, y, and z. Let's write some generic unit vector E1 plus B E2 plus C E3, or plus E4 plus E5. You can have any number of dimensions in your vector space you like, where A, B, and C are complex. And of course, a complex number, i.e., there's a real part plus I times an imaginary part, where I equals the square root of -1. Okay. And I've been careful here, when we did ON versus SON, ON are all the symmetries of the n-dimensional vector space. SON is just the ones that do not change the orientation, do not flip around some axis, okay? You might think that since this is the same setup, but with complex numbers rather than real numbers, it's the same thing. You might think that UN is just SUN, the special unitary group of n dimensions, plus flips of orientation. And in fact, you already know there's something called SU3 and there's something called SU2, so you're waiting for me to say SUN is just UN plus some flips. But that turns out not to be true. And the reason why is because if you think about what is a one-dimensional group, what are the transformations of a one-dimensional vector space, okay? 1D space. Well, let's look at real 1D space. That's just the number line, okay? It's just the real numbers. There's 0 at the middle. What can you do to it? Well, you can translate it, but we're not counting those, okay? By translate, I mean you literally shift over. That's certainly absolutely something you're allowed to do, but we're looking at rotations, or the generalization of rotations in 1D space. And there's the only thing you can do in a one-dimensional space to rotate it is actually to flip it, right? Is actually to exchange points on opposite sides with the same value. Ooh, that was pretty bad. I can do better. To exchange points on opposite sides with the same value. So, if this is -2, +2, they get flipped back and forth. That is something you can do. That's all you can do. So that is, in fact, O1, if you want, and that's just Z2. It's just a group with two elements. Either you don't do something or you flip it. Only possibilities. But what about 1D complex space? The complex numbers, right? Well, one complex number is kind of like two real numbers, right? You have the real part and you have the imaginary part. And any complex number, call it omega, it can be written as the real part plus the imaginary part. Or it could also be written as the length, which we can call r, times some angle, theta, e to the I theta. So r is the length, and theta is the angle in the complex plane. So in other words, if you write omega as, let's say, a plus ib, okay? So a is this, the real part, b is this, the imaginary part. You can write that equally well as r times e to the I theta. Now e, I gotta do a little bit of math here, sorry about that. E is the Euler constant, 2.718 ... the Euler constant. It's special for many reasons. It's a special number in mathematics. It's an infinite number. There's no simple way to write it down using a finite number of digits. There's no way to write it down using a finite number of digits. It has the wonderful feature that, I'll just tell you this and then I'll erase it. There's a function e to the x, okay? This particular number raised to the power x. I can take the derivative of that function with respect to x, ask what is the slope of that function. If I think what that function looks like, it's exponential growth, right? Exponential growth, something we all know about these days, e to the x versus x. It turns out that this is the unique function, other than just 0 everywhere, with the property that its derivative is equal to itself. If it were 2 to the x or 10 to the x, it would not quite have that property. There'd be another little prefactor out there. So e is a very special number. Good. Letting you in on that. And even better when you raise it to an imaginary number. That's what we're doing here, e to the I theta. So e to the I theta, theta is a real number. Theta is just this angle here. E to the I theta equals the cosine of theta plus I times the, oops, don't need that, I times the sine of theta. And here, in order for this formula to be true, theta has to be measured in radians, okay, in going from 0 to 2 pi. So if you plot, let's see if I can do this, probably not going to do this in real time. If you plot the cosine of theta, it looks something like this. Whereas if you plot the sine of theta, it will look something like this. Okay, that's sine theta, and this is cosine theta. So, again, this formula happens to work out. It's a miraculous, wonderful formula that is true if theta is measured in radians. So it repeats at theta equals 2 pi. This is theta equals 0, right there. And why is it so interesting? Well, remember when we did complex numbers squared? So when you have a complex number and you take its square, what you really do is you take its complex conjugate and then you multiply it. So by itself. So e to the I theta squared equals the complex conjugate. Let's see how I can write this. E to the I theta star times e to the I theta. E to the I theta star, I mean the complex conjugate just says change all the i's to minus i's. So this is e to the minus I theta times e to the I theta, which equals e to the minus I theta plus I theta, which equals e to the 0, which equals 1. So that's why this is such a nice little thing. This formula, e to the I theta, gives us a vector in the complex plane of unit length. Okay, that's why it's convenient to write any complex number as a length, r, times what we call the phase, or the angle, e to the I theta. Why am I doing this? Why am I going through all this effort? Well, we said up here in one-dimensional space, the orthogonal group in one-dimensional space is just flips. It's just Z2. It's either you flip it or you don't. Those are the only two things to do. In one-dimensional complex space, you have really two dimensions to work with. There's another thing you can do. You can rotate, okay? So the group U1 is actually multiplication of a complex number by e to the I theta. So if you have some complex number, so here's the real part, here's the imaginary part, and here is the complex number, call it omega, okay? If you multiply by theta, it keeps the length, by e to the I theta, it keeps the length constant. Let's zoom in here. The length stays the same, but you rotate by an amount given by theta. So if this is omega, this is e to the I theta times omega. So the set of all rotations in the complex plane is multiplications by e to the I theta, because e to the I 2 pi equals 1, right? We can write that. We did that, e to the 0 equals 1. That's also e to the 2 pi I, because you go back to where you started by that little picture up there. So anyway, the point being that in the orthogonal group case, in the real vector space case, ON is SON, just rotations, plus flips, whereas that's not quite true in the unitary group case. UN, in general, is SUN, which are just generalized rotations, as we expected, times U1, which is multiplication by a phase. So multiplication by e to the I theta. This is just called the phase. So anyway, all this is to get to the fact that this is a general rule, okay? It's not the same, quite the same thing as the orthogonal group case. There's a continuous set of transformations that we can take out of UN to leave us with SUN, okay? And S here stands for special, which is just, there's a fancy way of saying what that means, but it means not just multiplying by a phase. It means everything other than multiplying by a phase. Okay. And as before, we can calculate the dimensionality of SUN, as it is not going to be n. It is in fact n squared. Let me get it right. Yeah, I was going to say n squared minus 1, and that was correct. I should have just said it. Should have bleed myself. There you go. It goes up very quickly. The minus 1 is basically the U1, okay? The dimensionality of U1 equals 1 because it's just that one rotation. So the dimensionality of UN is going to be n squared. That's how many things you can do to n complex numbers. All right, where are we? UN, this is the rotations, complex vector spaces, very important because all of the matter fields of the standard model, all of the electrons and the quarks and the neutrinos, those are all complex valued fields. So the version that we have to use to operate on them, if there's some symmetry between them, will be SUN, not SON. Having said that, there is here secret fact that I'm not going to go into right now, but SO3 turns out to be almost, not quite, but almost the same group as SU2. They're both three-dimensional groups. We'll get in a little bit to why they're a little bit different. Not by a little bit, I mean not today. Someday down the road, we'll show you why they're different. The topology is a little bit different, is the answer. But the basic set of transformations looks very, very similar. Both three-dimensional groups. Okay. Good. So what I wanted to get to is the fact that these UNs, or SUNs really, this SUN, the real rotation here, this is where we get the SU2 cross SU3 of the standard model. The U1 is another symmetry of the standard model, and these are going to give us all the forces of nature, roughly speaking. The U1 is going to give us electromagnetism. Electromagnetism is a reflection of an underlying U1 symmetry of the complex valued electron field and positron field. The SU2 gets us the weak interactions. The SU3 gets us the strong interactions. Don't have time to do any of that today. Also, there's other secrets that will be revealed, but don't worry. I predict that next week we will get to exactly that. So I mostly wanted to get to you the idea of a group, and also the specific groups that we'll be dealing with. Z, Zn, SON, and SUN. These are our biggest, most famous groups. I can't, however, leave you without one more fact about symmetries. It is indeed the first fact about symmetries that many people know in physics, which is the connection between symmetries and conservation laws. Conservation was the very first topic, the very first idea that we had in this series. So it's nice to see the old friends coming back. And this relationship is summarized in Noether's theorem. Emmy Noether, famous mathematician of the early 20th century, and she said basically, well, it's a one-way street. Let's put it this way. Symmetries imply the existence of conservation laws. It's more subtle than that. Most conservation laws in nature do come from symmetries. There's a few tiny exceptions, but typically, if you find a conservation law, you should search for the symmetry underlying it. There are subtleties dealing with what kind of symmetry it is. Again, there's Noether's first theorem and second theorem. We're not going to get any of those things. The basic point is that that when you have a symmetry, there is a conserved quantity. And it turns out to be hard to explain why. Actually, Richard Feynman came up with what is probably the most transparent explanation of why Noether's theorem is true, which I'll try to reproduce, at least a little bit casually here. It all relies on the action principle. Remember, the action principle of least action says that there's this thing that you can calculate by integrating over time, something called a Lagrangian. I think Lagrangian depends on the position of some, let's just say a single particle. Let's make our life easy. It could be fields, right? And will be, but make our lives easy. Single particle has a position and a velocity, and it could also depend on time, but let's say it doesn't, okay? So this is the action. This is the Lagrangian. In field theory, we would also write the Lagrangian as an integral over space of the Lagrange density. Okay, we can do that. And the point is that if you considered all the possible paths the particle or the fields could take, what you would find is the actual physical path that obeys the equations of motion minimizes, or at least extremizes, the action. Okay, so it's like, kind of like, not exactly like, but kind of like if you considered all the trajectories of your system and you plotted the action, it turns out that the action would be a minimum at the actual physical trajectory. So this is all possible trajectories, like a particle sitting there without any forces acting on it, but just moving around in all sorts of directions, violating Newton's laws. That's a possible trajectory that we can contemplate, maybe a conceivable trajectory would be better. The physical ones are the ones that actually obey the laws of physics, okay? So Noether's theorem says that if you have a physical system that is described by an action like this, and by the way, not all systems are, but that's what we're going to consider right now. Most systems in quantum field theory, anyway, certainly are. So what it says is, let's imagine a symmetry is described by some shift of all the values. So we have x of t, the position as a function of time, and v of t, the velocity as a function of time, and you shift it to something parameterized by a parameter, let's call it epsilon, okay? So to some new value, x sub epsilon, of t and v sub epsilon of t. So what you're saying is, let's say that you are in a world where rotational invariance is obeyed. Okay, so you're in outer space, the Earth is not below you. You can rotate your coordinate system however you want, and the shift might be I just change my coordinates by rotating a little bit. Or in quantum chromodynamics, the theory of the strong interactions, QCD, maybe you change red quarks into blue quarks by a little bit. And this parameter epsilon tells you how much you change. And you're going to say, well, if it's like SU3, then I have many different transformations I can do. Yes, that's true. And what we're saying here is pick one, okay, and move it in one direction by an amount epsilon. So here is Feynman's argument for doing this, for deriving Noether's theorem. So here again we have trajectories, space, and here now we have time. So the actual physical trajectory maybe looks like this. There you go. This is x of t, and from that you could get v of t, okay? And call this point A, where you begin, and point B, where you finish. And he says, okay, now let's imagine doing this transformation. So I shift by epsilon, okay, to point C, right there, and then I do the same kind of trajectory, but I've shifted everything by epsilon. I've shifted everything by some amount, by some transformation, rotation, translation, some sort of internal rotation, whatever it is, okay? And I will label this point D. Okay. So here's the argument. There's a bunch of things you can sort of say about this picture. Let me move over the picture so I can say things about it, okay? One is, One is that the original action, S of A going to B, let's just write it as AB. Okay, the original path, this path right here, that's some value, and it better be equal to the action of the path going from C to D, because that path is just related to the original one by a symmetry. That is the assumption that we're making. There's a symmetry relating these two paths, okay? But there's another fact that's the sort of the obvious fact. There's another fact that is a little bit more subtle. But look, we're saying here that the action is minimized on the real path, which means if you do an infinitesimal change by a little tiny bit of epsilon, then the action won't change. Okay? So the total action on a path that is displaced from the original one by just a little bit is equal to the action of the original path, to first order, to the smallest approximation, okay? This is why it's subtle, and this is why it doesn't sound completely kosher, but you can make it completely kosher. Trust me on this. So what that means is, if this little displacement epsilon is infinitesimal, then the action associated with AB is also equal to the action associated with ACDB. That is to say, think of this little shift as an actual trajectory. It would be moving faster than the speed of light or something like that, but that's okay. It's just a conceivable trajectory. Think of the trajectory as going from A, moving over to C on that trajectory, then following the physical trajectory up to D, then going backward. Okay? Because that is only an infinitesimal change away from the original one, the action will be the same. Again, to a good approximation, and you can make it all rigorous if you want to. Therefore, what we can say is, it had better be the case that the action going from A to C, that little tiny trajectory, better be equal to minus the action of going from D to B. Just from what we said. We didn't say that the action on this path was 0, going from A to C. We didn't need to say that was 0. We just need to say that when you go A to C, then up to D, then back to B, the whole thing had to equal the original action. So there's a more general way for that to be true. Maybe it's 0, but it can be some non-zero value as long as it's compensated for when we go back from D to B. Finally, if you look at what the formula for the action here is, it's an integral over time, okay? So going from D to B is the opposite in time of going from B to D, going the opposite direction. So SAC equals minus SDB. That means it equals plus SBD. If you had gone in this direction, you would get the same answer. You would get minus what you got by going from D to B. So look what we found. Look at that. This is kind of fun. SAC, the action along this little path right here, is equal to SBD, the action of that little path right there. And indeed, it didn't matter where we picked our original or stopping points. All of these little paths, if you calculate the action on them, you would get the same answer. The quantity would be the same. So we say, therefore, SAC, or its generalizations later in time, is conserved. It's the same at every moment in time. So the action along a path that you get from wherever you are and going by this amount, by an infinitesimal shift, gives you a conserved quantity. Okay, that's Noether's theorem. The existence of a symmetry gives you a conserved quantity. It's sort of not at all surprising. In some sense, what a symmetry says is there's a direction in the space of all possible things that can happen where it doesn't matter, right? You can shift in this direction. It doesn't matter. It doesn't matter where you do your experiment, how you set up your orientation of your axes or anything like that. So the fact that it doesn't matter sort of morally corresponds to the fact that some number is constant. It would not change if you did a shift in that particular direction. This is just the formalization of that. So that's Noether's theorem. So it turns out this is kind of a big deal. So for example, space-time symmetries we have. So translations are, that's a terrible way of spelling translations. I'm just going to start from scratch. Translations are just shifts, right? Shifts in either space or time. Translations in space give rise to a conserved quantity called momentum. Makes sense. How many ways are there to do a translation in space? Well, there's X, Y, and Z. There are 3 of them, and there are 3 components of momentum. That works. Translations in time. Well, how many of them are there for that? There's only 1. And guess what? There's 1 conserved quantity. We call it the energy. Rotations. How many of them are those? Well, we have 3 axes in space. They're all real, right? So the number of transformations is SO3. The dimensionality of SO3 is 3. So there are 3 conserved quantities, and we call those angular momentum. And then we can go on to the internal symmetries, like the U1 symmetry that I told you we haven't really talked about in detail yet, but we will, of electromagnetism, is what gives rise to electric charge being conserved. And so forth. So this fact that Noether discovered, Noether's theorem, right there, which is that this quantity is conserved, is not just a mathematical curiosity. It's crucially important in all of physics. It gives rise to things that we care about, like energy conservation, charge conservation, stuff like that. Okay, that's all I wanted to say about symmetry. What we're going to need to do in the next video, the next idea, is get some payoff, okay? We've done 2 videos in a row on math. Math is great, but we're trying to understand the physical universe. So next time, geometry and symmetry are going to come together to tell us something about the fundamental laws of nature.